So now we begin question 4. Given that sine theta is equal to x, show that tan theta is equal to x over root 1 minus x squared, where theta is between 0 and pi over 2 radians or 90 degrees. So let's draw a right angle triangle here. And we can refer to this angle as theta. Or sine theta. Let's sine theta equal to x, or we say x over 1. Now sine is opposite over hypotenuse, right? So sine is opposite over hypotenuse. Opposite is x, hypotenuse is 1. So sine theta, let's x same as x over 1, right? We can now calculate, use Pythagoras theorem to calculate the adjacent to theta. So the length of the adjacent is root 1 square minus x squared. So 1 square 1 minus x squared, which means tan theta is opposite. Tan theta is opposite over adjacent, opposite x over adjacent root 1 minus x squared. Hence or otherwise determine the Cartesian equation of the curve defined parametrically y equal tan 2t, x equal to sine t. So let's do, alright, so y equal to tan t. So y equal to tan 2t, not 2 tan t, tan 2t. And we also have x equal to sine t. Now the double angle formula for tan is tan 2t, that's 2 tan t over 1 minus tan square t. Now we know that tan t, what was tan t? Tan t now if we should just compare tan t and sine, we are also told that tan sine theta equal to x, tan theta will be equal to this. The same situation. Same situation here. We are told that if sine t is equal to x, then tan 2t would be equal to the same thing. Alright, again, let me just redraw the triangle here. So sine x equals sine t. Let me call this t. So sine t is opposite over hypotenuse. So opposite would be x, hypotenuse would be 1, and this would be root 1 square minus x squared. So tan t, this means that tan t, let me just define tan t. This means that tan t will be equal to opposite over adjacent, that's x, over root 1 minus x squared. So we can replace tan t with x over root 1 minus x squared. Divide by, separate this, divide by 1 minus tan square t. So divide by 1 minus this square, tan square. So tan square would be what? X square over, and we square this, we get 1 minus x squared. Good. So continuing, we'll end up with y equal to 2x over root 1 minus x squared. Divide, and now I need to bring all this under one common one common denominator, so you divide by, common denominator would be 1 minus x squared. It's 1 over 1. I can multiply numerator and denominator by 1 minus x squared. Alright, so with that, and then we have a minus x squared here. Alright, so we end up with y equal to 2x root 1 minus x squared divide by 1 minus 2x squared over 1 minus x squared. And this will become 2x over root 1 minus x squared. And we times and we invert. So 1 minus x squared over 1 minus 2x squared. Alright, so we can simplify this a little bit. This is y equal to, so this is 2x times 1 minus x squared to the power 1 there. And in the denominator, we'll have 1 minus x squared root, well, same as to the power half, right? Into 1 minus 2x squared. And we can even go further. Notice the same base, 1 minus x squared. So we can subtract the powers. So we'll end up with y equal to 2x. And over here we have 1, here we have 1 minus 2x squared. And this base, if we subtract the powers, the base here is 1 minus x squared. If we subtract the powers, we're left with 1 minus x squared. 1 minus x squared to the power of a half, or same as root 1 minus x squared. I think that's the best we can do with it. We can rewrite it like 2x root 1 minus x squared over 1 minus 2x squared. Let's continue. Let u equal to 1 minus 3, 2, v equal to 2, 1, 5. Three-dimensional vectors. Calculate the lengths of u and v respectively. So the length of u, modulus of u, is the square root of x squared plus y squared plus z squared. Where for u, x, y, and z would be 1, negative 3, and 2 respectively. So square root, square 1, we get 1, plus square negative 3, we get 9, plus square 2, we end up with 4. That's a root 14. While the modulus of v, the exact same formula, square root of x squared plus y squared plus z squared. So square 2, we get 4, 1 squared, that's 1, and 5 squared, that's 25. So the modulus of v, or the length of v, would be root 4 plus 1 plus 5, that's root 30. Let's move on to part C. Find cos theta, where theta is the angle between u and v. So the formula for cos theta, so cos theta is u dot v over modulus of u times the modulus of v. Alright, so cos theta is equal to, now u, what was u again? U was 1, negative 3, 2. And the v was 2, 1, 5. Over the modulus, or the length, which we already calculate. Alright, for u, it was root 14. And for v, it was root 30. Alright? So the dot product, let's calculate the dot product. So 1 times 2, that's 2. Minus 3 times 1, that's minus 3. Plus 2 times 5, that's 10. All over the square root of 14 times the square root of 30. So what's 14 times 30? 14 times 30 That's 420, so it's the square root 420. So which means that cos theta would be equal to 2 minus 12, 110, 12 minus 3, that's 9 over root 420. Which means that theta, that's theta now, so theta would be equal to cos inverse 9 over root 420. Oh, I just seen with the question that was asked to find cos theta. So we are not asked to find the exact value of theta, that's cos theta. So cos theta, we stop here. Cos theta 9 over root 420. A point xy, a point xp, xy moves such that its distance from the axis is half its distance from the origin. Determine the Cartesian equation of the locus of P. So the best approach will actually to do a sketch of the situation here. Right, so we have our x-axis, we have our y-axis, here's the origin, 0, 0. So we have a point P, not drawn to scale here, so P is xy. Alright, so this is x, this is y. Alright, so point is moving such that the distance from the x-axis is half the distance from the origin. So here's the distance from the origin. The distance from the origin, that's the distance from the origin, right? Then we'll call this distance d1. Alright, and the distance from the x-axis is half the distance from the origin. Let me call distance from the origin. So distance from the x-axis, let me call this d2. Distance from the origin, let me call that d1. Alright? So d2 is equal to half of d1. Alright? So let's read this again. The distance, a point pxy moves such that its distance from the x-axis, here distance from the x-axis, I call this d2, is equal to half the distance from the origin. So here's a point P, distance from the origin, we'll call it d1. So d2 equal to half of d1, and of course we can multiply both sides by 2. So 2d2 equal to d1 for times both sides by 2, just to get rid of the fraction. Now if you consider the length of d2, got d2 here. The length of d2 is y. Alright, so d2, the length of d2 here, this vertical line is same as y, so d2 is y, so that's 2y. And the length of d1, if we use, remember this is x, this is y. So using Pythagoras theorem, d1 is actually the square root of x squared plus y squared. And of course, to get rid of the square root, we can square both sides. So if I square both sides, if I square both sides, two y all squared, so that's 4y squared. Square the right hand side, I'll just have x squared plus y squared. And if I group the y squared terms together, I'll have 4y squared minus y squared equal x squared. So this becomes 3y squared equal x squared. So we're asked for the Cartesian equation. So we have an equation in x and y. That would be it. The Cartesian equation of the locus. Part D, the line L, and L is 2x plus y plus 3, passes equals 0. the line L and the circle C has equation x squared plus y squared equal 9. Determine the points of intersection of the circle and the line. So this would be best solving using substitution. Now, the line equation, I'm just going to rearrange it. The line equation, if I leave the y on the left and group everything on the other side, y is actually minus 2x minus 3. So I'm going to substitute that into the circle. I'm going to substitute this now into the circle. X squared plus y squared is equal to 9. So I have x squared plus, and I'm replacing the y now with minus 2x minus 3, and I'll be squaring that, equal to 9. So all I did was replace y with minus 2x minus 3. So we end up with x squared plus, so square minus 2x minus 3 times itself. So square the first term, that's 4x squared, plus 2 times the product. The product is of the two terms here, that's 6x. So 2 times 6x plus, I square the last term, that's minus 3, I get positive 9, equal to 9. Alright, so what can I do now? So I would have x squared, well, x squared plus 4x squared, that's 5x squared. That's 5x squared, right? So that's 5x squared plus 2 times, that's 12x. And note, if I group the constants on the right hand side, I'll end up with 9 minus 9, which gives me 0. So of course I can factor out x. I'll have 5x plus 12 equal to 0. Equate both factors to 0. So we'll have x equal to 0 and 5x plus 12 is equal to 0, which means that x equal to 0. And if I solve this, subtract 12 from both sides, divide both sides by 5, by x equal to minus 12 over 5, or that's minus 2.4 or something like that. So I'll need the corresponding y values now. So recall that y, what was y again? Minus 2x minus 3. So recall that y is minus 2x minus 3. So if I substitute 0 for the x, I'll get y equal to minus 3. And if I substitute negative 2.4 for the x, I'll get y equal to minus 2 times the x, which is minus 2.4 minus 3. So y would be equal to minus times minus, that's positive 4.8 minus 3, which is what now? 1.8, or that's a 1 3/5, or so that's sorry, that's actually 1 4/5. 1.8 is 4/5, right? So I think I have that wrong. Or that's 9 over 5 if we want to use fraction. So the points of intersection between the line and the curve, so points of intersection between curve and line are when x is 0, y is minus 3, and when x is negative 12/5, now put them in fractions. When x is negative 12/5, y value is positive 9/5. Alright? So we have a circle and we have a line, which the line would intersect intersect the circle twice. Alright, let's move on. So we are now at question 5. Use an appropriate substitution. Use an appropriate substitution to find the integral of x plus 1 to the power third. So let me use let u be equal to, what's in the bracket? X plus 1, which means that du by dx would be equal to 1. Put 1 over 1, and if I cross multiply, I would have du equal to dx. So I'm going to use substitution. Alright, so I'm going to rewrite this. Since u equal x plus 1, this will be x plus 1. Well, x plus 1 to the third, so I will have u to the third. And I replace in dx with du. So now integration, we add 1 to the power. So add 1 to the power, we get 1 and 1/3, which is same as 4/3. 4/3. And we divide by 4/3. Alright, plus the constant. Now dividing by 4/3 is same thing as, so dividing by 4/3 is same thing as multiplying by 3/4. Alright, so actually multiplying by 3/4, that's 3/4 u to the 4/3 plus c, and then I just replace back x with u with x plus 1. So this becomes 3/4 x plus 1 4/3 plus our constant. Part B, the diagram below shows a finite region R, and we can see R shaded here, which is enclosed by the curve y equal x cubed minus 1, the lines x equals 0, y equals 0. Calculate the volume of a solid that results from rotating R about the y-axis. So the volume, when you rotate it about the y-axis, v is pi times the integral of x squared dy. And if we are rotating about the x-axis, it will be actually v pi y squared dx. Alright? But we're actually rotating about the x-axis, so about the y-axis, sorry. So that's the formula we use. So we need an expression for x squared. Now we know that y equal x cubed minus 1. We know y equal x cubed minus 1. So we need x squared. So what we can do is we can add 1 to both sides. We end up with y plus 1 equal x cubed. But remember, we want x squared. So how can we move from x cubed to x squared? We can raise both sides to the power of 2/3. Just raise both sides to the power of 2/3. So I'll raise this side to the power of 2/3. Now we know the law of indices says we can multiply the powers. So 3 times 2/3, that's 2. So x squared. And we have now into 1 plus y plus 1 2/3. So we can replace x squared with y plus 1 raised to the power of 2/3. So this is v, and by the way, the y limits, notice the y limits 0 and -1. So that's our y limit, so 0 and -1. Alright. So we replace x squared with y plus 1 to the power of 2/3. And we are integrating with respect to y. So again, we can use the formula, add 1 to the power. So with pi, alright, add 1 to the power y plus 1, add 1 to the power, we get 1 and 2/3. That's 1 and 2/3. 1 and 2/3, that's 5/3. And divide, remember how integration works. You divide by this new power. Now dividing by 3/5, dividing by 5/3, sorry, is equivalent to multiplying by 3/5, just times and we invert. So we actually multiplying this by dividing by 5/3, equivalent to multiplying by 3/5. Alright? Between the limits 0 and -1. Alright, so we're going to formulate two brackets. In the first bracket, we're going to replace, we're going to formulate two brackets. The first bracket, we're going to replace y with -1. The top number, well, the bigger value is 0, right? 0 is bigger than -1. So replace the y with 0. We end up with 3/5 times, place y with 0. So with 3/5 times 0 plus 1, which is just 1 to the power of 5/3. Now 1 to any power is 1. Alright, so that would be 3/5 times 1 really. In the second bracket, replace y with -1. Now replace y with -1. You'll actually have -1 plus 1, which is 0. Alright, so 0 to whatever power there, that's 0. So we just 3/5 in the bracket. So the volume is pi times 3/5, which is just 3/5 pi. Alright, cubic units. Units cubed, since we're talking about volume. Next question, given that the integral of f of x between limits 0 and a is equal to the integral of f of a minus x, where a is bigger than 0, is the same. Alright, so if try and understand what this is saying here. Notice we're saying that f of x, we can simply replace x with the top limit a. So here we have the integral of e to the x upon e to the x plus e to the 1 minus x. We have to prove it's equal to a half. Alright, so let's begin by the integral of e to the x upon e to the x plus e to the 1 minus x. We're asked to show that this should be equal to a half. Now, this says what we can do here is replace x with a minus x. What is a? The top limit. So we're going to replace x. Here the top limit is 1. So we're going to replace the x with 1 minus x. So this, we're going to rewrite the problem. 0, 1, e, replace x with 1 minus x. Alright. Over e, replace x with 1 minus x, plus e, and again we're replacing x with 1 minus x. So this is 1 minus, we're replacing the x here with 1 minus x. So it's 1 minus x. Alright. So we're replacing this x with 1 minus x. So we get 1 minus 1 plus x. So let's cancel. So this is just x. If we are replacing x with 1 minus x. Alright. Dx. Alright. What else can we do? Alright. So one thing we can do is we can rewrite function. So 1, 0. So here in the denominator we have e to the 1 minus x plus e to the x. Alright, so we have e to the 1 minus x plus, so some gymnastics here. Rewrite. Alright. So plus and minus. So it's same as saying e to the 1 minus x plus 0. But we can conveniently write the 0 as e to the x minus itself. Alright? And of course we can break it up. We can break up this. So we can write integral 1, 0. So this is e to the 1 minus x plus e to the x over well, let's write it better. Over e to the 1 minus x plus e to the x, and separate it, minus e to the x over the same denominator, right? 1 minus x plus e to the x dx. And as integral, we can write it separate, two separate integrals. So integral of this over e to the 1 minus x plus e to the x dx, minus, we have e to the x, e, so we separated it into two integrals, e to the x dx. Now if you notice what we have here, the second integral here, it's the exact same thing we have on the left hand side. Alright, e to the 1 minus x over e to the 1 minus x over e to the 1 minus x plus e to the x is 0, so we can move that. Alright, notice what we have here is the exact same thing. So we can group these, since these are like terms, we can group them on the left hand side. So on the left hand side, we actually have the integral of e to the x over e to the 1 minus x plus e to the x dx. I will bring this over, so it's plus the same thing. The integral of e to the x over e to the 1 minus x plus e to the x. So on the other side, we'll be left with just this, right? The integral of e to the 1 minus x plus e to the x over e to the 1 minus x plus e to the x dx. Alright? So we have two of the same terms. So we have two of the same term. Alright, so e to the x over e to the 1 minus x plus e to the x dx equal to, now notice what we have here is the term e to the 1 minus x plus e to the x over itself. So we're finding the integral of 1 dx. Alright? Now what's the integral of 1? Integral of 1 is actually x. And what were the limits? The limits were, well, the limits were 0 and 1. Let me just put in the limits. Alright, so the limits were 0 and 1. Alright, so integral of x between 0 and 1. Alright, so this is 2. Integral of e to the x over e to the 1 minus x plus e to the x dx. And of course, integrate x between 1 and 0, you end up with just x. Alright, so what we can do is times both sides by a half. So we're going to times both sides by a half. So we are left with this integral e to the x over e to the 1 minus x plus e to the x dx is equal to, so x between limits of 1 and 0 is just x. Alright, x minus 0, which is x times half, that's half x. Well, half. Well, that's 1, so 1 times half, which is half. Alright, so this will be, alright, this bracket what we actually have here is actually 1. So times half, integrate between, so evaluate between 1 and 0, so it's actually 1 minus 0, which is 1, which is equal to half. Alright, so that proves what we're asked to prove. Alright, let's move on to part D. Part D, an initial population of 10,000 bacteria grow exponentially at a rate of 2% per annum. By the way, 2%, that's actually 0.02, right? 2 over 100 per hour. Where y is a function of t, is the number of bacteria present t hours later. So solve an appropriate differential equation to show that the number of bacteria present at any time can be modeled by the equation y equal to that. Now, what is y? Y is the number of bacteria present. So give us a function. Alright, and it changes at 2% per hour. So which means that dy by dt, the change in the population over time. Alright? The change in the bacteria population over time is 2%. Alright, so it's 2%, 0.02 times the population, which is y. Alright? So dy by dt. So this means that if we should, before we integrate both sides, we want to separate y from t. So if we cross multiply, we'll end up with dy is equal to 0.02 y times dt. Alright, so group the y, so we can divide both sides by 0.02. If I divide both sides by 0.02 y, just extra step there. I'll divide both sides by 0.02 y, divide by 0.02 y. Alright, I'll end up with, no. Let me actually divide both sides by just y. So I want y by itself here. Divide both sides by just y. Divide both sides by y. I end up with that. So I end up with 1 over y dy equal to 0.02 dt. And now we can integrate both sides. Integrate 1 over y, that's log y. Integrate 0.02 with respect to t, that's 0.02t. Plus a constant. Now remember, log is base e, so the lower logarithm, so we can say what's in the bracket here, y is equal to the base e to the power 0.02 t plus c. Alright, rewritten, we can write it as e to the power of 0.02 t times e to the c. And c is a constant, e is a constant, so e to c gives another constant. We can call this constant a. So y equal to a times e 0.02 t. And how do we find a? So when the question tells us that at the beginning the initial population was 10,000. So when t0, y should be 10,000. Alright? So when t0, so substitute t equals 0, y equal 10,000 to find the value of a. So 10,000 and y is t0. So if t0, what we have actually as e to the power 0, which is 1. So a is 10,000. So therefore we end up with y equal to a, which is 10,000, times e to the power of 0.02 t. That's what we're asked to show. Determine the time required for the population to double in size. So remember, the initial population was 10,000. So if the population is to double in size, it means that y would now be 20,000. So replace the y with 20,000. So 20,000 equal to 10,000 e to the power of 0.02 t. And of course we can divide both sides by 10,000. Divide both sides by 10,000. So we end up with 2 equal e 0.02 t. And of course we can log both sides. So if I log both sides, I end up with log 2. And we know as a logarithm, we can put this power at the front. It's 0.02 t times log e. But remember, log e is equal to 1. So it's just log 2 equal to 0.02 t. Alright, to find t, we can divide both sides by 0.02. So we divide both sides by 0.02. Alright, so t is log 2 divided by 0.02, which is approximately 35, rounded to the nearest whole number. The time is in hours, right? So it's 35 hours. So the time would be 35 hours approximately. Question 6. Find the equation of the tangent to the curve that at the point where x is equal to 3. So the tangent is a straight line, so of course you want the gradient of that line. Now the gradient m of that line is given by f prime x, the derivative. Alright, so f prime x would be equal to differentiate, multiply by the power, subtract 1 from the power, so 3 times 2, that's 6x squared, 10x, and this is negative 1x, so that's negative 1, differentiate 12, you get 0. Alright, so substitute 3, so f prime 3, so substitute 3, we get 6 times 3 squared, which is 6 times 9, plus 10 times 3, minus 1. So m, or the gradient of the tangent, is what now? That's 54, 6 times 54, minus 30, that's 24, minus 1, plus 54 plus 30, that's 84, minus 1, that's 83. So the gradient is 83. So we want the equation of the line. Let me use the formula. Equation of tangent, or of any straight line. We can use the formula m equal y minus y1 over x minus x1 over x minus x1, where x1 and y1 is a point on the line. So m, we know m is 83. Y minus, we don't know y1. We know x1, x is 3. So x minus 3. Now we need the x coordinate for when x is 3. We need the x coordinate. So f of 3, let's find f of 3. F of 3, that will give us the x coordinate, the corresponding point for when x is 3. The corresponding y value of when x is 3, so that's 2 times 3 cubed. Now 3 cubed is 27. 2 times that, that's 54. Plus 5 times 3 squared. 3 squared is 9. 5 times that is 45. Minus 3 plus 12. That's what now? 54 and 45. That's 99 minus 3, that's 96. 96 plus 12, that's 108. So now the curve passes through, the line passes through 3 for the x and 108. So the x1 is actually 3, the y1 is 108. Using this formula here. Alright, so x1 is 3, y1 is 108. Alright, what can we simplify this? I guess we can cross multiply. Alright, so we end up with y minus 108 and 83 times x, that's 83x, and 83 times 103, let's say 3 times 80, 3 times 80, that's 140, times 3, so that's minus 243, right? 249, sorry, minus 249. 83 times 3, that should be 249. So we group, so we can add 108 to both sides, so we end up with 83x minus 249 plus 108. That's what, let's check this. Minus 249 plus 108, that's minus 141. So part B, calculate the left hand limit, which will be when x is less than 0. So left hand limit, that's this one. So replace x with 0, so that's 0 squared plus 2 times 0 plus 3, that's just 3. And here, the right hand limit, that's for when x is bigger than 0. Replace x with 0. That's a times 0, which is 0, plus b, that's just b. Alright? Next. Hence, determine the values of a and b such that the function f of x is continuous. So for it to be continuous, both limits have to be equal. Alright, for it to be continuous, the left hand limit must be equal to the right hand limit. So for it to be continuous, the limit x squared plus 2x plus 3 the limit of x squared plus 2x plus 3 as x approaches 0 must be equal to the limit of, that's the left hand limit, ax plus b as x approaches 0. Alright, and as x approaches this is 3, x approaches this is b. Alright, so b is equal to 3. If the value of b equal 3, if the value of b equal to 3, determine a such that f prime 0 is equal to f of 0 plus t minus f of 0 all over t. Alright, so we're going to plug f prime 0, we're going to plug, we're going to use both functions. So notice f of is a piecewise function, so notice f of x is, where is it? F of x is x squared plus 2x plus 3. F of x is also ax plus b. So x squared plus 2x plus 3, ax plus b. Alright, so this is for the right hand limit. Sorry, left hand limit, right hand limit. Alright, so let's, so f prime 0 is equal to the limit, and limit of t approaching 0 from the left. So what we'll end up with is replace x, the first, that's the first one, replace x with 0 plus t. So 0 plus t square plus 2 times 0 plus t plus 3, 2 times 0 plus 3 minus, and f of 0 will be 0 square plus 0 plus 3. So it's just 3 that we have here, which would cancel with that, right? All over t. Alright, so this will be t squared plus 2 times t divided by t, which should be equal to t plus 2. Let's take steps. So let's take some steps here. Alright, so this will be the limit as t approaches 0. So limit as t approaches 0. And as t approaches 0, then this would be equal to 2. And let's do it for the other function. Right hand limit when ax, the right hand limit, so we use a function this time. Now we're using ax plus b. Alright, so f prime 0 is also the limit. And we're doing the right hand limit this time. So this time we're replacing again, in this function, we're replacing again x with 0 plus t. Alright, so the a times 0 plus t. So it's a times 0 plus t plus b, but we are using the value of b to be 3, so plus 3, minus f of 0, replacing x with 0, we're just left with b, which is 3. Alright, all over t. So 3 minus 3, that's 0. So we end up with here. So this is actually at divided by t, that's just a. Right, so we end up with a is equal to 2. Right, so we have a in this case, and we have 2 in this case. The left hand limit equal the right hand limit, so a is equal to 2. Alright, let's continue. Seems to be the final question. Use first principle to differentiate f of x equal to root x with respect to x. So the first principle's formula says that f prime x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. It's the first formula. So we have a limit as x approaches 0. Now f of x plus h, replacing x with x plus h. So that's root x plus h minus f of x, which is root x over h. Alright, so we can try and multiply numerator and denominator by the conjugate of the numerator, the third here. So the conjugate will go what now? Root x plus h plus root x, multiply the denominator by the same thing, root x plus h plus root x. Alright, so end up with limit as x approaches 0. The denominator will not change. Actually, it's h times root x plus h times root x. Now we're multiplying the numerator by its conjugate, so we can just take the square of each term, right? So root x plus h times root x plus h, that's actually just x plus h. And in the final term, root x minus root x times root x, that's just minus x. And of course, when I do the expansion, the middle term will cancel. So remember that a minus b squared, when you multiply a binomial times its conjugate, a minus b times a plus b, you end up with a squared minus b squared. So you square the first term, this will be like the a, this will be like the b, right? Like the a, like the b, square the first term, minus square of the second term. First term root x plus h, second term root x. Now we'll get these always square. So, alright, so we end up with the limit as x approaches 0. X take away x, that's just h, or 1h, over h, bracket, root x plus h, plus root x, h into h, that's 0. That's 1, sorry. And we can substitute 0 for the h now, so we end up with 1 over root x plus h, which is just root x, plus root x. Right, so we end up with, did I make an error here? And this becomes 1 over 2 root x. Root x plus root x, that's 2 root x. That's the end of the paper.